It's 10:10. Oh my gosh, you guys, it's 10:10. We have to hurry and start before it's 10:11 and we're late. So I have a couple announcements. There are CTNT t-shirts and you should have one because think in 2 years, 3 years, when you remember fondly this conference, you'll have a t-shirt and that's forever. You can see Alvaro.
Not only that, today there will be vintage t-shirts available.
If you want to pretend that you were here some other time and remember, be like, 2016? Yeah, I guess I had a good time. I think it was good. I also want to say, I think many of us lecturers have been putting some stuff online, so I haven't really looked at what other people did, but for me, I put my slides from last time, so I literally just took scans of the stuff I wrote down, so now they're online as lecture 1, and I also have a series of exercises that I will add to every day after I finish my lecture and therefore know what I can exercise you on. So you can click on exercise, you'll see, lecture 1, and then just keep scrolling, you'll get to lecture 2, and then later keep scrolling, you'll get to lecture 3. And then finally, yesterday I was at the evening session, as were, I think, many of you, and it was super fun. So if you didn't come, you don't want to miss out on that. I come back at 7, but a bunch of people were already here. So come hang out. What else do you have to do? You don't even live here. Okay. What are we going to do today? So yesterday I called today odds and ends, and today I know what's going to happen today, so I will tell you. I will start with a little very short recap from last time. Then I will say a little bit about why is this happening to us? What is my goal? And why do we talk about function fields and number theory? Well, not why. I mean, they're really interesting, but one reason. And then there will be something about completions and entire functions, which I'll define what that is, so it's okay if you don't know. And then after that, so that was all kind of non-Archimedean stuff, and then I'll move on to characteristic P stuff, do additive polynomials and FQ linear polynomials. And then I think that we will know enough to start on lecture 3 on the actual stuff that I'm interested in. Okay, so let's just recap a little bit, right? I always think, when you watch TV, sometimes you're watching a Netflix marathon and they still tell you previously on this show, and you're like, yeah, I just watched it, but it's okay. Let's do it, right? So previously, because a lot happened, and here's what I want you to remember. So we had a field, okay, and this is last time I talked a lot about kind of all non-Archimedean fields, but really this guy, FQ brackets T, the rational functions with coefficients in FQ is a finite field with Q elements, is really the field that I care about. And inside of it, there is a ring of polynomials. Okay, so those are our basic objects. We defined on this field evaluation, and it's perhaps best understood on quotients to be the degree of the bottom polynomial minus the degree of the top polynomial. And then from that, we define an absolute value, which again, it's perhaps best understood on quotients to be Q to the degree of A minus degree of B. Okay, so now we flip them back. That's the same as Q to the minus evaluation of X. And Q is the cardinality of that field. I said any constant greater than 1 would give you an absolute value, but Q is particularly pleasing because it's the cardinality of that field. And then we went over some properties of non-Archimedean fields. And I just want to remind you of what are, to me, the highlights. Non-Archimedean fields, the S goes here. Okay, so the ultrametric inequality is not only cool to say, but awesome. And leads to the fact that every triangle is isosceles. And then this weird stuff with balls. So balls are disjoint or contained in each other. So it's a very strange land. That we live in. So that's what I went over, and I just want to tie up a couple loose ends. There were questions that some people answered, but I'm not sure how much of a good job I did to like affirm their answers. So I'll just like put this on the record. So it is true. Some true facts today. If K is a field of characteristic P, then every absolute value is non-Archimedean. So someone had said that, but I just want to like affirm it. So this field that we're working with is characteristic P. So also remember Q is some prime P to the R. So P is going to be my prime. So that's true. And actually, like reading about that, I found out like another fact, which I thought was interesting. So every Archimedean absolute value comes from, okay, you take your field K and you embed it into C, right? So if K has an Archimedean absolute value, then it follows that you can embed it into C, and then the absolute value of an element is the absolute value of that element after you've embedded it to C, and I'm going to put infinity there. That's the usual Archimedean absolute value on C, and I believe that maybe there's a power, so maybe it's just straight up that absolute value, or maybe it's that absolute value squared. So really, it's the Archimedean absolute values that are rare and strange. There are so many non-Archimedean absolute, they're like everywhere. Like you just like find them on the ground and like throw them out. It's the Archimedean ones that are special. Okay, so that's a recap of what happened. And we did all this because I think everybody should know this. So now you know this exists. Yes?
Does alpha have to be 1 or 2, or can it be any positive power?
Okay, so different people differ, and it depends how they define an absolute value. I think that the way I define an absolute value, it has to be 1 or 2. But if you read, like, for example, Pete Clark's notes, he defines an absolute value to be, like, a little different. Like, my thing that I call an absolute value, he calls a norm. And then for him, it can be any power. So, like, I don't really, like, this is just, like, a kind of parenthetical remark to give you some ideas. So I don't want to get into, like, this. But it depends exactly how you set things up, and you should be careful.
Okay.
Yeah. So he writes this theorem with alpha, like any positive number. But then his definition of absolute value has a different constant that I don't remember.
In some books, they have said that if it means the same topology, then the value is equivalent.
Yeah. So, but for me, like if I want the triangle inequality to be true, then like you have to be careful. So anyway, I don't want to get into that. I refuse to answer this further. Okay. So why are we doing this? I'm going to start like to tell you what my purpose is here today in life. Why? Why is this happening to us? So there is a number theory and analogy between what we call on one side the number fields and on the other side the function fields. And the kind of like, and if you Google number field, function field analogy, there will be like 1 million hits and 1 million of these tables. And I recommend especially Poonen has a table in some of his notes, and it's like pages and pages of number field stuff on one side and function field stuff on the other side. And anything you care about, you can see like its friend on the other side. Yep.
What is the infinity subscript on that absolute value of x?
Oh, it's so.
Like supreme
No, it's just a normal Archimedean absolute value. So on Q, right, if I had picked Q instead of this polynomial because I'm a strange person, then we would see that on Q, there's an absolute value for every prime, the p-adic absolute value, and then the usual Archimedean one, we usually call it like the infinity one, like P is the prime at infinity. So that infinity is just to talk about Archimedean here. It's not supremum or anything like that. That's a good question. But anyway, going back to my number field, function field thing, most of these tables start with, on the number field side, the ring Z, the integers, your friends. And on the function field side, the ring FQ brackets T, the polynomials, which are now your friends. And then the rational numbers Q and the rational function field FQ brackets T. And so that's why, so for me, like historically, how it happened in my life is that I was encouraged to start working on this side to establish analogs of some theorems we had on that side. And that's like a very fruitful area of study to try to go between, like, be inspired from the function field side and do something in number fields or vice versa. Okay, so this is why I'm interested in, and okay, why like these ones? Because they're the simplest ones. So some people study finite extensions of Q number fields, and some people study finite extensions of FQ round brackets T, which are also called function fields. But I focus at the bottom, which is hard enough for me. And why is there such an analogy? Like, you know, you're like, okay, you can put them next to each other, but why? To me, the most satisfying answer has been just because it works. I can give you many reasons, but it felt to me reading about this yesterday was that a lot of it was like, there were parallels, and then we made up reasons why there were parallels, right? So mostly it's because it works. Many theorems have analogs on either side. And why should that be true? Well, maybe if you start thinking about it, both Z and FQ brackets T, the base rings are principal ideal domains. So that's nice. Once you go to finite extensions, if you look at the integer rings on both sides, they're not PIDs, but maybe I'll call them like those base rings. On both sides, there'll be Dedekind domains, which is not as nice, but it's still very nice and more than you can ask from a ring. Usually, if you want to get fancy, you can talk about the completions of Q and FQ round brackets T are all locally compact fields. That comes up in proofs, so then the same kind of phenomenons show up on both sides. What is that? They're both Z and FQ brackets T have finite unit groups, right? Like once you just start thinking of stuff you care about on both sides, then there's a lot of things that are kind of similar enough that the kind of theorems you can prove about Z or, extensions of Z or, orders and theorems about FQ brackets C, they have analogs because the same kind of structures are true on both sides or exist on both sides. Zeta functions on both sides, etc. And I'll just leave you with a buzzword. Both Q and FQ round brackets T are what we call global fields as opposed to local fields. And so, but I feel like people noticed they were the same and then called them both global fields rather than like there was some idea of global field and then they were like, oh, those are dumb. But anyway, so you'll hear people say, oh, this is like about global fields or this is about local fields. And when they're talking about global fields, they're talking about these guys and their extensions. So anyway, that's why I'm interested in these. And for us, right, I just gave many things that are true on both sides. But for us, the goal is to do some class field theory. But it'll be very gentle. And to have an analog of elliptic curves on the function field side. So that's the direction in which I'm trying to take us. So to fill in, these columns, but with class field theory stuff and elliptic curves on this side and Drinfeld modules on that side. Okay, but it's worth learning about function fields because if you find out like a nice theorem, you can always check if you can prove it in the function field setting. And then you have 2 papers. Or you just, I taped it too well. Okay, I'm just going to tear it out. Come on. Okay. Or if you're Drinfeld himself, you write 1 paper that's about both, and it's difficult to understand. Okay, so that's why. That's where we're going. That's our future together. But first, we have to finish some background material. We have to earn it. So let's finish this completions and entire functions, which is where I was going yesterday. So we'll seamlessly zoom back to what happened yesterday. So I can't remember if I said this yesterday or not, so I'll just say it again. So I'm going to define some stuff. I mean, there's 3 of them. It's definitions. So I'm going to let K be a field. So for now, any field, any absolute value on K. And then the first thing that I want to define is say that I have a sequence of infinity numbers. Each of them are in K. This sequence is Cauchy if for every positive epsilon there is a number n such that xn minus xm in absolute value is less than epsilon whenever n and m are both greater than big N. So what I'm saying is if I want stuff to get close together, then I just have to go far enough away, and far enough away, all of them, right, like any NM that are big enough, they're all like bunched up together like this. And if you saw the definition of a Cauchy sequence before, this is it. It's not different. Okay, the second definition is I will say that K is complete if, with respect to this absolute value, with respect to this absolute value, if every Cauchy sequence converges to an element of K. Okay, so here, all I'm saying is that these elements bunch up together a lot. The problem is that, like, they bunch up, they get closer and closer and closer together, but there might not be anything there, right? They might be all getting closer to something that's not existent. So Cauchy sequences are sequences that are doing, like, everything they can to converge, but sometimes they don't, just because the limit doesn't exist, right? But not in the sense of, like, oscillating or going to infinity, but, like, in the sense of, like, not being there. So a field is complete if whenever a Cauchy sequence is doing its job, there is something for it to converge to at that place. Okay, and then the last thing that I want to define in this definition, I gave you I said there would be 3. So I can, if I have a set S inside of field K, I will say that this set is dense if every open ball around every element of K contains an element of S. Okay, and in symbol, sometimes that's easier to understand. For all x and k and for all epsilon greater than 0, the ball around x of radius epsilon, which I defined last time, intersects with S non-trivially. So S is everywhere. You can't get away from it. You can't put it at a distance. It's as close to you as it wants. Okay, so I will use these to define the completion of a field, because, and why do I need that? Is because FQ brackets T is not complete, right? So my problem, why all this? My problem is that this field that I love is not complete, and that's bad, because then I'll have sequences and they won't converge through no fault of their own. And so I want to define a place where that's not true. A better land. So let me just prove this, because it's not so difficult. Okay, so consider the sequence xn, and the elements of xn will be like this. Okay, so if I write this out, that's like t to the minus n plus t to the minus n plus 1 plus blah, 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 all the way to 1. Okay, and this is really in this because I can write it as a ratio of polynomial. This is t to the n plus t to the n minus 1 all the way down to 1 divided by t to the n, right? So this is a ratio of polynomials for every n. So I have a bunch of these rational functions. Okay, so my first claim is that this sequence is Cauchy. So I'm going to fix some epsilon greater than 0, and then I have to find an n. So I'm going to let n be such that q to the minus n is less than epsilon. Okay, this is always possible, no matter how small epsilon is, because q is bigger than 1, I can make like a fraction 1 over q to the n. That's tiny, tiny. You can take n to be like the ceiling of minus the log base q of epsilon if you must, no. Okay, then and I'm going to take little n to be strictly less than little m to be strictly other way. Oh, this is going to mess me up. Okay, well, I'll try it out. So I definitely want little n and little m to be bigger than n. Okay, and I just want them to be different. If little n and little m were the same, that would be 0, and of course that would be less than epsilon, so I don't care about that. And without loss of generality, I'm making n be the bigger one of m. Okay, so that's not what's important here. Okay, so what happens? Well, if you remember, right, these little elements are like 1 plus, like sort of like more and more negative terms. And because little n is bigger than little m, it's like it has more negative terms. So this will end up being t to the negative n plus t to the negative n plus 1. Okay, and then t to the negative m negative 1, right? Because the rest of the stuff is canceled out by the xm. And this would be less than or equal to the maximum of these absolute values by the ultrametric inequality. But I know that I get equality when the valuations are different, right? And these all have different valuation because they're all different degree. So I actually know that this is going to be the max of the absolute value of t to the minus n, t to the minus n plus 1, right, t to the minus n minus 1. Okay, and I know what all these numbers are. This is the max of q to the minus m, q to the minus n. See, I knew this would mess me up. N plus 1, okay, q to the minus n minus 1. Okay, and who is the biggest? This guy is the biggest because this exponent is smaller. Okay, but whatever, it doesn't matter because m is bigger than n, so this is less than q to the minus n, and that's less than epsilon. Right? So these elements are getting closer and closer. For any epsilon, I can get them to be close enough by just making sure that they end far enough. Okay, so this should converge to some number that I'm going to call x infinity, which should be the sum from minus infinity to 0 of t to the I, right? I mean, like, you know, even before I did all this, right, you look at this and you let n go to infinity, you're like, well, I'm just going to plug in infinity there, and that will give me my limit. Right? So this should go to some element like this, and it feels right? Except, like, that's not an element in my field, so that's the problem, right? So it's not really the sequence's fault, it's like the field's fault.
Sorry. So this now equals to 1 over 1 minus t minus 1.
1 over 1. Oh, did I pick a bad example? I picked a bad example. Oh, well, sorry.
I think we can use like countability and uncountability.
Yeah, there should have been a Cauchy sequence that there definitely are, and then I picked one. I was like, oh, this one's easy, so you can just do that. But you're right, that does converge. Wait, 1 over, so this would go, yeah, no, you're right, this would go, okay, so this would go to 1 over t over 1 over t minus 1, or it might be 1 over 1 minus t, but anyway, whatever, I can like clear the t's on both sides. Okay, so that's false. So, okay, we all have to have use your imagination.
I squared the exponent.
Oh, I could do that. Okay, imagine that I did all this with squares, and then that wouldn't work, I think. Okay, so instead, do xn to b. There's so many. No, I is minus n to 0, and then I think that one doesn't represent a rational function when you let n go to infinity. And the same argument would show you that it's Cauchy. But that's not in there. Yeah, thank you. Wow. Listen in your calculus class, you guys. It could save you some embarrassment. The point remains, though, that I want a place where every Cauchy sequence converges because I don't want to worry. And this is called the completion, or I mean, the smallest place where this is true is called the completion of my field. So in this case of the field FQ, round brackets T. Okay, and so it's not a definition, but what you should think morally is that K hat, the completion of K with respect to some absolute value is just K union the limit of every Cauchy sequence. And this is not the definition, okay? There's like, what does that even mean? What about if two Cauchy sequences go to the same limit? How would you even know? Like, I'm not saying that's a real definition, but that's just what you should think. It has exactly K and all the limits and nothing else in it, right? It doesn't have more. Okay, and you can look up, I'll leave it as an exercise, look up the real definition. Which is like basically an exercise in like, do you have the internet? Do you know the URL to Google? There's many of things, right? And the definition, it's everything, like everything in math. It's what you need to do stuff, but it doesn't tell you like why you did this. So you did this for that. That's the reason. Okay, so for us, the completion of this field with respect to this absolute value is just FQ double brackets 1 over T. So the stuff that's in here can go from minus infinity to some finite number up top, AI, AN, T to the N. So they're all the rational, I don't know, they go that way. They go the negative way. So if you think about it, right, like in calculus, you kind of think of Taylor series, like getting higher and higher powers of T or X or whatever, and that's okay. But we want the other thing. We want lower and lower powers of T because those get small. So, right? So it's like in R, for example, like pi, which is like 3.14159, right? Like this can go on because it gets tinier and tinier. So you can add like more and more of these digits and that remains a real number. But you don't want to add like more and more of these numbers on that side. Like if you go infinity in that direction, like that gets big, right? So it's the same kind of thing here where you're cool with like lower and lower powers of T. That's kind of like the expansion, like a decimal expansion that goes infinitely in one direction but not the other, because you can go in the small direction, not the big direction. Anyway, so fun things about this, which like I ended with last time because I wanted to end with a bang, but now today we've earned it. So let K hat be a complete field with respect to a non-Archimedean absolute value. Then the sequence Xn is Cauchy if and only if the limit Sn goes to infinity of xn plus 1 minus xn goes to 0, which is false in the real numbers, so, or in a non-Archimedean absolute value. So this is amazing because it's a lot easier to check. And then 2, the one that I told you that we're actually going to use, a sequence converges if and only if the limit of its terms is 0. And last time I put the absolute values because I panicked, but you don't need the absolute value. Just the limit of the terms is 0. Okay, and we'll use this one a lot. Like, we're going to define entire functions which are given by power series that converge, and it'll be so easy. It will be so easy. Calculus 2 here would be a lot better. All your students would love this theorem. Okay, because you know that's not true, right? I mean, like, hopefully you've graded and, like, put big X's through. Like, and we try. I taught calculus and I try to call it like the divergence test, right? To be like, you can only use this to check for divergence. It's the divergence test. And then I would say on the exam, by the divergence test, it converges. There's nothing you can do. There's nothing you can do. Yeah, but here it works. So you try to draw it out of your students. Like, were you thinking of maybe a p-adic valuation? They're like, please let me leave. Okay, so let me go back to our analogy, because now we've added a row to the table. We've added the third row, right? So we have z, and for us that'll be, I'm trying to start making you think that this is okay. And then we have Q, and that's this field, and you're like, that's cool, you know, like we have like whole things and then fractions of things. And then in the classical setting, you complete Q with respect to its usual Archimedean absolute value, and you get R. And for us, we get this field. Here. And now I'm going to go right away and fill in more lines of this table because the story is getting long. So where I will really want to live is in something like C. Why do I care, right? What are the nice things about C? It is complete and algebraically closed. I want it all. Like, I want all the numbers to be in my field. I want all my sequences to converge and all my polynomials to have all their roots. I don't want to be missing anything, right? So that's what's nice about C. Now, it's not very hard to go from R to C, right? You add I. It's like degree 2, right? So you could think of, like, actually C as the algebraic closure of R, so it's not that bad. It's going to be a little worse for us. Okay, so I'm going to expand. This will have more rows. So you start and you're like, okay, well, this is complete. Right? I just made it, but it's not algebraically closed. Right? Like there's no like roots of t or something like that, right? T to the 1 over m, right? So you're like, okay, well, I'm just going to take the algebraic closure. That worked on this side. That wasn't so bad, right? So I'm going to make this, the algebraically closure. The algebraic closure, so this is algebraically closed, but not complete. So it's like those cartoons, right, where like something's coming out of the floor and you go on one corner, but then like the other one springs out and you're like, oh, you run, and then so you're like, well, I'm going to complete that, right? So I take the algebraic closure and then I complete that. And then maybe the size of the bracket tells you this is complete and algebraically closed, right? I didn't write like a series of hats going down all the way. Okay, so this is complete and algebraically closed. So we're finally there. So there's an extra step that you have to take here. This field, I will call it C infinity. Okay, or sometimes some people just like denote it like C like this, or blackboard bold C infinity. I mean, like, there's not really a standard notation for this field as there is for the complex numbers. And often this one is K infinity because we think for some reason that's not like for some reason, like it's stupid, but for some reason that I'm not telling you, that this valuation is like kind of the valuation at infinity. And maybe the 1 over t gave it away a little bit. But one either annoying or awesome fact is that this is infinite. So C infinity is an infinite dimensional over K infinity. So it's not like here where C over R is dimension just 2. So it's pretty simple. You can get your hands on this C. That C is a little tougher. And it's bad because it's complicated, but it's actually good because there's going to be a lot more space. So here, I'm going to define kind of rank 1 elliptic modules and rank 2 elliptic modules, which you already know as the exponential function and elliptic curves. So I'm just using fancy words to confuse you, right? But that's it, right? There's only like room for like rank 1 and 2 lattices in C because of this dimension count. In my world, my better world, in which I hope to take you, I can have lattices of any rank, because this is infinite dimensional. And so this allows us to actually solve problems for more R's, for more values of R. How much time do I have? I have 10 minutes. This is great. So anyway, so that'll be our players. And a lot of the time, you should just think that you're in C infinity, because I want everything to work. But also at the same time, C infinity is very difficult to think about, so you can think about this guy. It depends what you want. Do you want to worry or not worry? And so I want to give you a definition / theorem that we'll use. Definition. I don't want to call it a theorem. I'm going to call it a proposition. It's not that big of a deal. Okay, so I'm going to let f of x be the sum n is equal to 0 to infinity a n x to the n, and I'm going to let my an's be in C infinity. So now I'm just working like with all my numbers. Okay, we say f is entire if it converges for all x in C infinity. So this is like Taylor series, right? A Taylor series that converges for every element of R, or in my case, C. So this is the main way in which I will define functions for you, by series, and then we'll check if they converge or not. But it's very easy because of this divergence theorem, which is now a convergence theorem, right? So this happens if and only if, right, it converges for all C, if and only if the limit as n goes to infinity of the valuation of an divided by n is infinite. So to check convergence for every element in C infinity, you just have to take this like cute little limit, which is really not that big of a deal. And this is just one instance of a kind of bigger theorem that gives you, right? So this is kind of, I'm saying the radius of convergence is infinite. So there's a secret radius of convergence theorem here, and you could have a function that doesn't converge everywhere, but kind of converges on small elements and diverges on big elements, and that'll be in the exercises. So you'll figure out like a criterion like this, and then show if the valuation of x is, too big, then it diverges, and if it's too small, then it converges. And then I gave you two of my favorite power series to find like the radius of convergence. It's called the order of convergence. And so anyway, you can have a lot of fun with that. But for me, I'll be defining functions that are entire mostly. So, this is the one that I really need. Okay, so the proof I will leave for you. It's not super difficult. So I'll leave you to deal with the exercise. And I'll just set up in the last 5 minutes our next topic. So next up, so we just finished all the Archimedean stuff. So now we're going to do characteristic P stuff. And more precisely, additive and FQ linear polynomials, which are very characteristic P things to talk about. Okay, so I'll just give you the definition in my last minutes. Okay, so let K be a field and P of X be a polynomial with coefficients in X. then P is additive if P of x plus y is equal to P of x plus P of y for all x, y in K. Okay? It is what it is. I hope the word additive is evocative for you and you're like, yeah, that's what I expected. Okay, and why did I say that's a very characteristic P phenomenon? Well, if we take, for example, Q, right, the only additive polynomials are P of x is some constant times x, so it's not very interesting to talk about. You don't want to spend a whole bunch of time on this. But in characteristic P, we immediately get a ton of them because we have that x plus y to the P is equal to x to the P plus y to the P. So immediately, right, anything that's like to the P or to the P squared or to the P cubed or will be additive. So any polynomial that has only, linear terms, x to the P squared, x to the P cubed is going to be additive. So like then there's a ton more polynomials there. Okay, that's not an if and only if. So also, okay, so let me give you like a fun example that's due to, at least it's in David Goss's book. So let P of x be in F3 of x, so the coefficients are in F3. Then you can check that P of x is x to the 6 plus x to the 4 plus x squared plus x is additive. Okay, so it's not just, right, a linear term and then an x cubed and then an x to the 9 and then an x to the 27. So maybe that's surprising. But it's an additive polynomial, but it's a kind of additive polynomial for a dumb reason. So once you start playing with it, you'll be like, Christelle, come on. But there's many additive polynomials over finite fields. Okay, so we'll talk about them, we'll characterize them, right? So this is over a finite field. I'll be talking about my field, FQ brackets T, so I'll have like the T of my coefficients and then the X of the polynomial. So we're going to start to have like many variables going on. Okay, but I will reserve that for tomorrow and instead just give the other definitions so you can start thinking about it. Because I think if you sleep on a definition, it helps. So let K be a field. And this time I will require that FQ be contained in my field. Then P of x, which is a polynomial with coefficients in x, is FQ linear if P is additive and P of zeta x is zeta px for all zeta in FQ. And so if you have these two conditions together, it means that any linear combination with coefficients in FQ kind of pops out of your polynomial, right? If you have P of zeta x, cx plus zeta y, that will be, which is what what FQ linear should mean. And so these polynomials will be very important to us, so we'll spend a little bit of time at the beginning of next lecture characterizing them, talking about their roots. That'll be the important part of it. The roots are going to be wonderful. They're going to be additive groups in the case of additive polynomials, and they're going to be FQ vector spaces in the case of FQ linear polynomials. And then from there, when we talk about the Carlitz module and the Drinfeld modules, we'll get like really nice properties of certain things that they define, and it will be amazing. So that's where we're going. Next time we will have the correlates module, so it's going to be a big day. All right. Thank you.